This is a historical moment for me. We just opened the representative office of the Fields Institute in Shanghai a few months ago, and this is perhaps the first official such act. So I am going to be the speaker of that historic event. So I have to say, Dietrich, Ivy, John, Doris, Yichao, I'm very proud to be here in your name, in front of all of you, with a great organization who is a long-time friend of mine, which is New York University, Shanghai Campus. So I decided today to speak. I changed the subtitle. If you see what I wrote, you see that I like to talk about the dawn of the social fintech, and I'll explain what that means. But I think as a way to relate to Chancellor Tong and your philosophy background, I decided to use a different subtitle, which is the 4 elements of Aristotelian philosophy: air, earth, water, and fire. And we're going to be dealing with all of them. For that, I want to have the audacity of giving you, experts, a brief history of finance. I am known to be audacious. So I want to make a point. If you look at the evolution of finance, and I'm going to look at the 20th century, I don't care what happens before then. You probably see, this is the graph of the Dow Jones Industrial Index. You probably see the 1929 crash right there. This is perhaps the most interesting part of the history, not very often talked about. And this is what happened around the time of the oil embargo. The markets were horribly volatile. And by the way, we're at the Volatility Institute, so how can I not mention this? This is what caused the Institute to start. The origin of the Institute goes back to the oil embargo and what it did to financial markets. The result of that was well known: derivatives, the 1987 crash, September 11, the Enron collapse, quantitative easing, structured credit, 2008, and so on and so forth. But the lesson I want to draw from here is that financial risk drives financial innovation. Where are we now? Well, Kyoto 1997 introduced a very interesting mechanism, which is the CO2 exchange, whereby emitters and capturers could exchange securities with each other. It was mentioned in the previous talk. It's something which is introducing a new security in the market. And I want to draw your attention to perhaps the most important, in my opinion, the most important part of the Paris Agreement, which is Article 2.1c. 2.1c says, I'm paraphrasing, that there's going to be an attempt by 193 countries to make finance flows consistent with a reduction of greenhouse gas emissions. John, this is why climate risk is more important than water. Sorry to tell you. Nothing like this exists for any of the other sustainable development goals, only climate. Political reasons, scientific reasons, I'm not going to get into that. But this is fundamental for what we experience, which is that climate risk is now driving financial innovation. You wish it was water. Me too. But that's the reality of what we deal with, and that's why my talk today is about climate. There's a very interesting article also in the Paris Accord, which today is perhaps the year of that agreement. That's Article 6. Article 6 basically talks about international cooperation and how countries can buy credits from each other. Article 6 has, in fact, 3 main sub-articles. Article 6.2, which talks about cooperative approaches. You don't have to read it. Okay, this is not the time to read legal documents. I just want to mention it to you. Article 6.4 talks about mitigation, and Article 6.8 talks about other non-market approaches. What this means is that there is a market for emissions, as it was mentioned in the previous talk. Today I'm going to get very deep into that because I'm a mathematician. We tend to get deep into things, and I'm going to tell you the perspective of me, your humble servant, mathematician, how we see these things happening. So, if you look at the Paris Accord emission targets, I'm giving you a summary. This is some of them. How did these numbers come up? Let's read this very quickly. United States, they're going to reduce emissions by 26 to 28% below 2005 levels by the year 2025. European Union, 40%. China, India, Canada. How did these numbers come up? Did they come up because of scientific considerations or by bullying each other into getting different numbers agreed upon? I let you decide. Okay, I let you decide. But I'm a mathematician, so I couldn't care less how these numbers came up. I want to try to tell you my perspective on these numbers. And this is a very typical chart that is, well, it's actually true. Many people use this. You say, well, these are the countries who emit CO2. And guess what? Number one is China, of course. So that's why China is in the news, right? But everybody who knows anything will tell you why. It's a pretty big country, right? So then some people have said, I don't like this table. I'm going to look at this other table. This is the emissions per capita. Then suddenly China disappears. A very interesting country shows up, Canada. Actually, Canada is number 7 in both tables. Is this the right way of looking at emissions? Well, let me be a mathematician. This is Paul Erdos, a very famous mathematician. He said something very interesting. You know, I'm a mathematician. When I go to restaurants, people ask me to split the bill because they say, I'm a mathematician, I know how to divide. Well, he has a very good sentence. He says, a mathematician is not someone who knows how to add. It's someone who knows when to add. And we know, mathematicians, that both of those tables are wrong. The absolute numbers are interesting. Dividing by population, if you have a calculator, you can do it, but they have no meaning. So I set myself a target, which is, what should those numbers be? What should those numbers be? So there's a paper we wrote, I'll just mention it here. This paper that I wrote with 2 of my students. One is actually from Shanghai University, the other was from University of Toronto. And what we did is, let me try to understand what drives emissions. And then, yes, people drive emissions. You can see population is there, it's factor number 3. Urban population drives it too, so does electricity production, GDP, and this and that. This is important because emissions are a function of these things. If it wasn't for this, we want to reduce emissions, just kill people. That will do it. Well, that's not in the works. We're not going to do that, right? Or say Canada, you want to reduce emissions, we give Quebec to France, and that will reduce emissions. Well, that's not in the works too. So we need to understand what emissions are a function of. By the way, linear regression does not work. We had to use something slightly different. Support vector regression. It doesn't matter. I didn't come here to lecture math. I came here to tell you how math thinks about these things. And once we know that, then you can do something pretty interesting. If I say what your emissions budget should be, not the one that they negotiated in Paris, no, the one that I did in my computer. If you do that, then I can look at your actual emissions. And then I can see how your emissions have changed over time. And these are the numbers for 16 countries. I made sure that you cannot read the names of any of the countries in those charts. This is not why I'm here. I'm not here to tell you whether Italy or the UK or Australia are. What do these numbers mean? Well, you have a country like that one that seems to be having emissions that just keep on increasing over their assigned baseline. By the way, this assignation is not done by politicians, it's done by mathematics. Okay? Then you have another country that seems to become greener. Their emissions are coming down with respect to their emissions as assigned by mathematics. Do you think this would mean something? Right? Perhaps when all the countries, they gather around and they start to renegotiate the targets that they set themselves in 2015, because they're not going to make it. Okay? If anybody's going to make it, it's maybe China. That's my opinion. So I'm not the mathematician at that time. Okay? So when they do that, maybe these things should be taken into consideration. Perhaps. By the way, we did the same thing for methane. Methane emissions are important too. Methane is actually worse than CO2. We don't produce as much of it, but it has a global warming potency which is 80 times that of CO2. By the way, do you know why CO2 is a greenhouse gas? Most people don't know. It's the same effect as when you put your food in the microwave. The plate doesn't get hot, but the food gets hot. You know that? That's physics. Yeah, the radiation makes the water spin. Exactly. The water molecule spins when you hit it with radiation. So does CO2. Methane spins even faster, right? By the way, oxygen doesn't spin, nitrogen does not spin. Okay. By the way, textbook or homework question, why don't we care about water, which is a very, very big warming agent? Because it rains. It doesn't stay in the atmosphere. That's why. So, but CO2 stays there for a long, long time. Methane does not stay for a long time. Good for us. It oxides after 30 years, becomes CO2. So it actually decreases its potency. But it still is a major concern. Okay. So what we did is we did something similar, and John worked with my graduate students. And what we did is we found something very interesting, which is most countries are actually above the baseline of their methane emissions. And again, this is mathematics talking. This is not politicians talking. This is interesting. Most countries are. Do you know this school that was so good that every student was above the mean? No, you don't know the joke. Okay, oh, you're not mathematicians. Well, here I have that school. Almost everybody is above the mean. The thing is that when you do baselines like the way we do it, you can actually have everybody above the mean. Okay, so anyway, but let me switch to water. I need to talk about water a little bit because John is here. Everybody knows John Cherry, winner of the Stockholm Water Award 2022. So here's, this is a very interesting case, and this is for you, John. This is Kenya. And in Kenya, a very interesting project happened, which was a company, I believe a Dutch company, brought 880,000 family water filters. And what that did had a very interesting effect because people started to drink water not like that, but like that. And this is a carbon trade because they analyzed and they saved 2.7 million tons of CO2 per year, which at market rates, you mentioned that, would be anywhere from $20 to $100 million per year. Water filters. There is a new financial market out there. It's beginning. And I think we need to study it. Yes? Okay, so I need to talk about fire now. And for this is a very interesting business case. Actually, it's the most interesting business case because here's the case of a tribe in Northeast Australia in the Savannah region of Australia. And savanna fires have a very bad way of behaving, which is that they tend to happen when they burn the most during the dry season. So this tribe created the Naeliga Corporation in 2017, and the idea was to burn the savanna preemptively. When they did that, which is called controlled burning, they saw that the area decreased by 33%, the area burned, the grass and the wildlife were starting to come back. It was all good, but they got paid for this. They got paid because the emissions, the CO2 emissions dropped by 40%. The numbers are not public in terms of how much money you are in total for a trade like this. My guess is about $1 million a year. Again, another example of a financial market which is just out there, it's just beginning. Okay, and yes, China has their own. We've been at the carbon exchange in Shanghai several times. We have a relationship with them. Philips is actually an affiliate member of the carbon exchange in Shanghai, and we expect to do more of that. This is all very interesting, but the most interesting part is, let me tell you how artificial intelligence has to do with all of this. You see all these documents popping up there? This is all the documentation that is needed to do a trade like this. You can say, for $1 million a year, of course I'll do all these documents. But now the question is, do you know how long it takes to do these documents? Probably 3 months. They need to be audited every year, right? And that means that every time you're going to be doing this, it takes a long time. And by the way, do you know the commission? Do you know how much it costs to do these documents? The commission is typically 50%. So if you're going to make $1 million for this, you're going to have to pay about $500,000 to the consulting company that does all of these things for you. So how can you do this faster? Well, large language models, that's how you will do it faster, okay? But that's a different talk for a different day. Because what I want to do now is, let's see how all of this can be put to work to find a solution, a nature-based solution. And planting trees is a solution which is out there. There's a very interesting problem when you do that, when you do forestal development, which is, how do you know the cost and the revenue parameters? You have to now think of this as an investment problem, like the one that people have been talking about in this conference. This is a very particular investment problem, which is, if I'm going to plant a forest, how do I know? The cost, you know how much it costs you to buy it and to plant it. That's very well known. But what is the income coming from that? Right? So for that, I have here, it's all data science. I took the liberty of making a mock-up database of, it's only 4 years, but this is a, I don't know how to say this tree in Chinese, but this tree is aboriginal of the Shanghai area, camphora, and the camphor tree. Okay, and the GPS location is actually a forest just outside of Shanghai. So this could be real. It's not, I made it up. It could be real. But if I have a database like that, then this database can be, has to be studied. You don't get credit for the biomass, you get credit for the different parts of the biomass. The dry biomass is treated in one way, above ground and below ground are treated different ways. You have a dead, you have live biomass, soil, you have trunk, branches, leaves, all of that is how you get paid. It's a very complicated expression that tells you how this biomass is worth. And that and more things is what you do with machine learning. We have a method of doing machine learning analysis during work with my colleagues to calculate the amount of CO2 that leads to the investment value of this. Today, this is done with approved protocols and audit statements and disclosure documents, but very soon this is going to be done with machine learning. So get ready. This market is coming and it's going to be very efficient. And by the way, you can replace that database with satellite images or even drone images. And then, well, the use of AI is going to be just higher. But these are things that you can do very fast in real time. Okay? And when you have a situation like that, you know the location of your trees, you know the type of tree, then you can come up with the cash flows of your investment project. And this is a way to decarbonize and make money at the same time. Okay? Now, the interesting thing happens when you're trying to do this in a place where you don't have data. Well, there again, machine learning comes into place. You don't have all of that information, but you can use nearest neighbor methods to actually find what the value of those projects are. So this is the new finance that's coming to us, all related to carbon markets. Yes, I wish we had something similar for water, but we don't, John. This is just what we do for climate. So to end my talk, let me move to the next question then. If this is how it works, if you want to have impact, what should you do? Now, the question there is now completely different because we need to know what will have consequences. Now, for that, what I have to do is borrow from the talk of Marcos López de Prado over lunch, where he told us about causal discovery, because that's how you do it. Okay. Now, today, climate risk is things that we know. We know CO2 warms up with the sun radiation. Okay. They are the known unknowns that we don't know. This could cause temperature to go up. This could cause ocean levels to go up. Okay. And then it's the unknown unknowns, and there, of course, we don't know. That's how you do risk theory. I don't have time to do risk theory today, but I do want to tell you that there's a big difference between association versus causality. Because, as I said earlier, I could decrease my emissions by giving a province to my neighbor, but that is not the intent. We need to be able to lower emissions in different ways. And for that, we have to understand the difference between association and causality. Association is what happens at the same time as, and causality is what happens because of. Okay? And I like to do a fallacy approach to causal reasoning, and for that I use the book of Steve Koonin, Unsettled. You may have read the book. I think it's a great book for counterexamples. For mathematicians, it's great. So he says something, I just took an example. He argues that global fruit production has significantly increased in the 20th century as the world experienced warming. So he thinks warming is good because it led to global food supply. And he says this is good. Well, let me show you how causal inference would argue. You have CO2 and you have hunger, right? Well, it is true that food has, and global food supply chains have decreased hunger. We also have engineering that has helped us improve our food supply and also created agromechanics that mixed with a transport led to the increase in food supply. And by the way, this creates CO2. So in the language that was developed by Marcos this morning, the fact that CO2 and hunger are correlated does not mean that there's any causality between the two of them. In fact, these are terms that are called confounders. That's how these terms are called. And the bias that we heard over lunch here is precisely what causes, in my opinion, Steve Koonin to make a logical mistake, a mathematical mistake in his book, Unsettled. And this is a crash course on causal inference. This is how you call the different terms in a causal graph. This is what causes what. You have mediators, colliders, ancestors, and descendants. And this is how you do logic. This is what we heard at lunch. And that's how you can actually take action. If you have the causal graph for anything, then you know touching what node will have impact on a different node. And that's the holy grail. That's what we want. Yes? So we did this in the context of emissions, again with my students. I always work with my students. And this is the causal graph that we found for emissions. I'm missing what's called the weights. I'm missing the betas. We're still working on this. I will tell you the betas next year. Until then, I thank you very much for your attention.
Thank you.